Learning about waves always requires a thorough understanding of wave behaviors. By behaviors, I mean all the interesting things that waves can do when they interact with media. Waves can travel through objects, reflect off of surfaces, resonate with atomic particles, and bend from one medium to the next. Reflection, refraction, and other wave behaviors explain a lot of the mysteries behind how we perceive everyday waves like sound and light. But there are other less familiar wave behaviors that we should learn about. Diffraction is one of those less obvious wave behaviors that play a big role in our perception of waves. Diffraction describes the change in a wave's direction as it travels between or around barriers. It's similar to reflection and refraction in that it involves a change in the direction of waves when they encounter a change in medium. Reflection describes how waves bounce off of surfaces. Refraction describes how waves bend as they pass through the boundary between two different media. Diffraction is different. In diffraction, waves actually bend around objects that they encounter in their path or bend through openings in between two barriers. You may have seen diffraction occur when water waves travel through a gap in a wall or a jetty. The waves bend outward from the opening in the wall and fan outward from the gap. To see how diffraction really works, we'll first take a look at sound waves. It's easy to imagine sound waves bending around obstacles. Have you ever tried to speak with someone who's standing in an adjacent room? Even if that person isn't in your line of sight, they can usually hear you speaking at a reasonable volume. That's because your sound waves bend around the edges of walls and doorways until they travel toward that person. The same thing happens when that person speaks back to you. Diffraction of sound waves is one big reason that animals can communicate over long distances. Think about the places that most animals live. Forests, mountains, prairies, and swamps all have tons of vegetation and land features that block visual communication. Animals can still get in touch with each other because their vocalizations get past all that. Their sound waves bend around those obstacles and travel toward their intended audience. Some animals are better at long-distance communication than others. Elephants, for example, can communicate over miles of land in order to keep their herds together while they're traveling. People haven't always known about elephant communication because they vocalize at such a low frequency that we can't even hear it. Elephants use infrasound, or sound waves with frequencies of less than 20 hertz. These low-frequency, long-wavelength sounds actually diffract around objects to a higher degree than other higher-pitched sounds. In fact, the amount of diffraction that occurs in any wave is dependent upon the wavelength of that wave. Let's think for a minute about why this might be true. In order for a wave to bend around an obstacle, the wavelength of the waves must be larger than that obstacle. The same is true for waves traveling through an opening. The wavelength must be larger than the opening if it is to pass through the opening and come out on the other side. For any given obstacle or opening, waves with longer wavelengths bend more than waves with shorter wavelengths. If the wavelength is smaller than the obstacle or opening, then diffraction barely happens at all. Some animals don't want diffraction to happen to their sound waves. Bats, for example, need their sound waves to come back to them so that they can tell where they are in the dark. They use echolocation to navigate and to find the flying insects that they eat. For this reason, bats need to make sound waves with very small wavelengths or very high frequencies. These sounds are too high-pitched for humans to hear, and they're called ultrasound. They tend to have frequencies of more than 20,000 hertz, and so they have wavelengths of such a small size that they don't diffract around objects like trees and flying insects. Instead of diffraction, bat sounds are reflected back to the bat's ears, so essentially they can see in the dark. People have known about diffraction in sound waves for a long time. But what about light waves? Scientists used to think that light wasn't capable of diffraction at all. They could hear sound waves bending around obstacles, but they couldn't see light waves doing the same thing. It turns out that because light waves have such tiny wavelengths, they can only diffract when they pass around obstacles or openings that are less than 1,000 nanometers wide. This is because wavelengths of visible light are between 380 and 760 nanometers. So we don't see diffraction of light waves nearly as often as we do sound waves. However, we do utilize the diffraction of light to help us understand the molecular structures of crystalline solids. For instance, we know that diamond and graphite have different atomic structures because of a technique called X-ray crystallography. X-rays are electromagnetic waves, so just like light waves, they can diffract when they're given the right conditions. Scientists pass X-rays through the crystalline structures where the spaces between the atoms are small enough to allow diffraction of the waves. The X-rays bend in many directions, forming an interference pattern that scientists can read. The pattern is carefully studied in order to understand the exact arrangement of the atoms inside of the crystal. Back in 1952, scientists even used X-ray crystallography to figure out the structure of DNA. So even though we don't see the diffraction of light on a daily basis, we can at least appreciate that it impacts us in other ways. Diffraction describes how waves bend or change direction as they travel around the edges of obstacles. Diffraction occurs in water waves, sound waves, and light waves. But the amount of diffraction depends on the size of the obstacle or opening in relation to the wavelength of the wave. Waves with larger wavelengths diffract more than those with smaller wavelengths. Therefore, infrasound is good for long-distance communication, while ultrasound is better for echolocation. Diffraction of light and other electromagnetic waves only occurs when the openings or obstacles are very small. For this reason, the structure of molecules can be studied using the interference of diffracted X-rays.